In this video, we're going to cover the fundamentals of probability. Now, there's a lot to cover for today, so here's the agenda. In math methods, there are multiple types of probability. This video is going to cover the core principles that apply to all the types of probability, no matter what. All the topics are chaptered in the description below, so feel free to jump around to whatever topic you're looking for in particular. Otherwise, let's get into it. The simplest examples in probability come from sample spaces. The sample space is simply the list of all possible outcomes for a given scenario. If we want to find the probability of a specific outcome or a set of outcomes, then we simply take the number of desired outcomes and divide through by the total number of possible outcomes. The shorthand of this is to write PRX equals x divided by n, where x is the number of things you want to happen and n is the total number of things that could happen. If I have 7 red marbles and 3 blue marbles, then my probability of selecting a blue marble is going to be 3 out of 10. I have 3 desirable outcomes over 10 total outcomes. Similarly, I have a 7 out of 10 chance of selecting a red marble, which brings me to the next law of probability. All the probabilities in a given scenario need to add up to 1. This is most commonly written as a plus a prime equals 1, or rewritten as a equals 1 minus a prime. A is the probability that we're interested in, and a prime is everything except that probability. This idea here is actually used quite a bit in probability, but it's most commonly used in probability distribution tables. A probability distribution table looks something like this. Just a quick note on notation. Capital X is known as the random variable. You can think of this as sort of like a stand-in for a particular scenario. For example, capital X could be the random variable that describes the number of points you could win in a game. 1, 2, or 3. Little x is a stand-in for the outcomes of that event. In this case, we had a game where we could score either 1, 2, or 3 points, so little x is going to stand in for either 1, 2, or 3, the outcomes of that game. And so the statement PR capital X equals x simply means the probability of any given event occurring, and those probabilities are listed in the bottom row. This table is telling us that there's a 20% chance of scoring a 1, a 30% chance of scoring a 2, and a 50% chance of scoring a 3. And you'll also notice that all those probabilities add up to 1. Let's have a look at how these probability distribution tables are actually used in exams. This question here uses a probability distribution table. But what you'll notice in this case is that all the probabilities listed are in terms of p, and our goal is to figure out what p could be. So what do? Well, there's only one thing we can actually say concretely about any probability table, and that is that all the probabilities have to add up to 1. This gives us an equation we can solve. So we'll just go column by column, add them all up, and then equate that to 1. This particular example will turn into a quadratic. It isn't uncommon for areas of study to overlap like this, so if you need to revise quadratics, then I've left a link in the description for you. Either way, this one was tech enabled, so we can use a CAS to solve this, giving us the solutions p equals 1 over 5 or p equals negative 1. Now, here's the thing. That solution does appear in the multi-choice list, but it's not correct. The reason is simple. Probabilities cannot be negative. They can only be positive or 0. Hence, the only real solution to this is going to be p equals 1 over 5. The union and intersection are two terms that come up quite a bit, not just in this area of study, but also all the other ones as well. Suppose we have a Venn diagram of two sets A and B inside a total sample space. The intersection of those two sets are the common elements that are shared by both A and B, the middle part of that Venn diagram. The intersection between two sets is mathematically expressed like this, with an intersection symbol. When you're doing questions about finding the intersection, it will usually be described as find the probability of A and B, and usually denotes the intersection between two things. The union of two sets is everything that belongs to either A or B. When you're solving questions about the union, it will usually be phrased as find the probability of A or B, or being the union. The union of two sets can be found by finding the probability of A, the probability of B, and then subtracting the intersection of A and B. Here's why. This diagram represents the probability of A, and this diagram represents the probability of B. If we were to simply add those two areas together, then we would double up on the intersection. And that's why we subtract the intersection from the equation. It doesn't mean that the union doesn't include the intersection. It simply means that if we didn't subtract the intersection, then we would actually be accounting for it twice, not just once. Let's try an example. We're told to find the probability of drawing either an ace or a heart from a standard deck of 52 cards. The use of the word or means that we're trying to find the union of those two things, not the intersection. And we can find the union of those two things using the equation we found earlier. We just need to know what each of those terms are. The probability of drawing an ace can be found by using sample spaces. There are 4 total aces in the deck, and there are 52 cards in a deck as a whole. So the probability of drawing an ace is going to be 4 divided by 52. You could simplify this to 1 over 13, but it's preferable if you do the simplification later after you've done all the arithmetic. It just makes life easier. Next, the probability of drawing a heart. There are 13 hearts in the deck and 52 total cards in that deck. So the probability of drawing a heart is going to be 13 divided by 52. Now for the intersection. There's only one card that is both an ace and a heart, and that is the ace of hearts. And so if there's only one card in that deck of 52, then the probability of drawing the ace of hearts is going to be 1 over 52. Now that we have all the terms, we're just going to sub into the equation and simplify. And that's going to give us an answer of 4 divided by 13. 2 events are considered independent if one event occurring has no impact on the probability of another event occurring. A classic example of this is a coin toss. If I tossed a head on my first toss, then the probability of me tossing a head on the second toss is still 50-50. Just because I tossed a head on the first toss does not change the probability of me tossing a head on the next toss. If 2 events are independent, then the intersection of those 2 events can be found by multiplying the probability of the first event with the probability of the second event. Using the above example, if I want to find the probability of tossing 2 heads in a row, then I simply need to find the probability of tossing a head on the first toss, which is 1/2, and tossing a head on the second toss, which is also 1/2. If I multiply those 2 things together, I'm going to get a quarter. Again, I want to highlight that this equation only works for independent events. The exam is usually pretty good about this. It will literally say in the question whether or not the events are independent. In fact, we'll have a look at an exam question where this was covered once we cover probability tables, so skip ahead to that if you like. 2 events are considered mutually exclusive if there's no intersection shared between them. That is, PR A intersection B equals 0. All this means is that both things cannot be true at the same time. If we're trying to find the probability of drawing either an ace or a king from a standard deck of 52 cards, then we can use the union equation. We just need to know what each of those terms are. The probability of drawing an ace is going to be 4 divided by 52, since there are 4 aces in the deck and 52 total cards. And the probability of drawing a king is going to be also 4 over 52, since there are 4 kings in the deck. And then we look for the intersection. And then we realise that there is no intersection between ace and king, because there is no ace of kings in the deck. King and ace are mutually exclusive events. So the intersection is going to go to 0, and we just add those 2 probabilities together, giving us either 8 over 52, or when you simplify it, down to 2 over 13. Sometimes the probability of an event occurring depends on events that occurred earlier. This is what we mean by conditional probability. For example, if you see dark clouds in the sky, then the chance of rain is likely to be a lot higher. And if there are clear skies, then the chance of rain is going to be a lot lower. And so, if you want to find the probability of some event A occurring, given that some other event B has already occurred, then you need to find the intersection of those 2 events and divide through by the probability of B, the conditional event. Here's a typical exam question which covers this exact thing. For starters, we're told that the probability of rain on a Monday is going to be 0.21. But we're also told that the probability of rain on Tuesday depends on if it rained on Monday. And finally, we're supposed to use that information to figure out the probability that it rains on both days, that it rains on both Monday and Tuesday. This question is about conditional probability. So the conditional probability equation will be important here. The only question now is, how do we use it? Well, a good place to start is to write out all the probabilities that we're told in terms of math equations. So we can start with the probability of rain on Monday. We know that's just 0.21, so we're going to say PR, rain on Monday, equals 0.21. Nice and simple. We also know that the probability of rain on Tuesday is 0.83 if it rained on Monday. This is a conditional probability. Rain on Tuesday is the thing that happened, and rain on Monday is the conditional thing. So, now we have a conditional probability equation, we just need to start filling in the blanks. We know that it equals 0.83, and we also know that the probability of rain on a Monday is 0.21. So let's put that in the denominator. All we have to do from here is rearrange to get the intersection on its own. Just a quick note, it doesn't matter what order you put the intersection in. If A intersects B, it's also just as valid to say B intersects A. It doesn't matter the order. For example, you can say that a card is both a heart and an ace, and you could also say it is an ace and a heart. It doesn't matter what order you say those statements in. Two more notes on conditional probability. Firstly, if your events are independent, then PRA intersection B can just be replaced with PRA multiplied by PRB. And since PRB appears in both the numerator and denominator, they cancel out. And so what this means is that PRA given B is the same thing as PRA. It doesn't matter that B occurred. These events are independent. If the events are mutually exclusive, then that intersection will become zero. And so therefore the conditional probability will also become zero. For example, if you want to find the probability that the card is an ace, given that it's a king, then that probability should be zero because, well, it can't be both a king and an ace. Tree diagrams are a strong tool that we can use to solve conditional probability questions. So here's what they look like. Each of those branches represents a different choice or a different outcome. Each of those branches are labelled with the probability of taking that branch. Those probabilities are conditional probabilities. They're conditional based on the previous branch you took. That's how we get several branching paths. The probability of taking a path all the way to the end is written at the end. That probability is the intersection of all the events that occurred before it. And that probability is found by multiplying all the probabilities along the path. This tree diagram tells us that PRA intersection B can be found by multiplying PRA by PRB given A. Let's see how we can use this to solve the previous example. So we're looking for the probability that it rains on both a Monday and a Tuesday. So let's start filling out the tree diagram. And so we'll start filling out the branches for Monday. The probability of it raining is 0.21. Therefore, the probability of it not raining must be 0.79. This is because all possibilities need to add up to 1 for a given event. Now we have to draw the branches for Tuesday. The probability of rain on Tuesday, given that it rained on Monday, is going to be 0.83. And so we're going to go down the rains on Monday branch and then down the rains on Tuesday branch and label that with 0.83. And as before, if we have a 0.83 chance of rain, then we have a 0.17 chance of not raining. So we'll write that one out as well. And so we're just going to do the same thing for the other branches. This time we're going to look at what happens if it doesn't rain on Monday. We're told that the probability of rain on Tuesday, if it didn't rain on Monday, is going to be 0.3. And therefore, the chance of it not raining on Tuesday is going to be 0.7. At this point, we've filled out all the branches. Now that we've filled out all the branches, we can pretty much answer any question we want. If we want to know the probability of raining on both days, then we just go down each of the branches that have rain on both days. There's only one of those. And you just multiply along the branches. Well, what happens if I want to find a more complicated probability, like the probability of it raining on either Monday or Tuesday? Well, we actually have two options here. The first option is to go down each path that has rain on either Monday or on Tuesday. We simply multiply along each of those branches and then add the results together. Alternatively, you can save yourself some time and find the one branch that doesn't end up in rain and then subtract that probability from 1. This is because all the outcomes need to add up to give 1. And if you only have one outcome that doesn't end up in rain, then you can find that one a lot quicker than you can find the other 3. Probability tables are another tool that we have at hand to make life a lot easier. These tend to be more useful for simpler experiments or ones that rely on pure arithmetic, like this question here. We're told what the probability of A is, as well as the probability of a few choice intersections. But before we dive into that question, let's figure out how the probability table works. The outer edges of the table represent the random variables A and B. We also denote their complement probabilities A' and B'. The inside of the table represents the intersection between the two events. And so if you want to find the probability of A intersection B, then you'll find that in the A column and the B row. The outside of the table represents the probabilities of each event occurring, with the bottom right-hand corner always equaling 1, since all the probabilities have to add up to 1. The idea is that any row or column need to add up to give the final entry. For example, PRA intersection B plus PRA' intersection B gives you PRB. This also works vertically, and it also works outside the table on those outer edges too. These are the key features that we'll need to know about probability tables to solve this question. First things first, we can fill out that table with the known values. We want to find PRA intersection B, but we currently have no way of getting there. So let's find some unknowns first. We can find a prime by subtracting 0.4 from 1, since the bottom row always has to add up to 1. That's going to give us 0.6. Now we can find the intersection of a prime and b prime by subtracting 0.2 from 0.6, since this column needs to add up to become 0.6. And that's going to give us 0.4. Here's where it gets a little bit trickier. It doesn't look like there's a clear path to get to A intersection B. We need something else. And that thing comes from this statement here. A and B are independent events. If A and B are independent events, then the intersection of those two events can simply be rewritten as PRA multiplied by PRB. But that actually applies to all the intersections. So the fact that we know that PRA prime intersection B equals 0.2 is going to be really helpful for us. PRA prime intersection B can be rewritten as PRA prime multiplied by PRB, and we know that that equals 0.2. We also know that PRA prime equals 0.6, and so all we have to do is rearrange to get PRB on its own, and that's going to give us PRB equals a third. Now that we know this, we actually have two options. First, we could just ignore the table and simply find the intersection by multiplying PRA by PRB, since we know both of those terms. Alternatively, you can just keep using the table. We know that PRA intersection B plus 0.2 needs to equal a third. So you can rearrange to get PRA intersection B on its own and then simplify that result. Just be aware you want to make sure that your decimals are rewritten as fractions. That makes life a lot easier when you're trying to simplify these down. If you want to error check yourself in the exam, then doing it both ways is a good way to do that, because both methods should give you the same answer. In fact, if you really want to be confident, feel free to fill out the entire table and then check every row and column. They should all add up to give the appropriate results, but that's a little excessive. If you found this video helpful and would like to see more, I actually have written versions of these lectures available for free on my website. Just click the link in the description below and it'll send you to my website.